Okay, so ladies and gentlemen, good day all. So in today's video, we are going to look at the concept of nomenclature of organic compounds. And from the word nomenclature means naming. So in this video, we are going to look at how we are going to name coordination compound. And don't forget that in my previous video, we is on coordination compound and transition method. So please, if you didn't watch those videos, you should go back and watch them. And I will attach the link of those videos to this video. And you can check them on the comment box. So first, coordination compounds consist of central metal ion bonded or surrounding ligands. So generally, in the case of this coordination compound, they are made up of two major components. The central metal ion surrounded by the ligands. And this is how the transition metals looks like. The entire box is called coordination sphere. So in the coordination sphere, you have the central metal ion and the ligand. So the central metal ion, it is Fe here, and the ligands are the ammonia. So this is what you call coordination sphere. And we also have counter ion. Counter ion are always found outside the coordination sphere. This counter ion can be positive and it can be negative. So, but from this example, the counter ion is negative because we have chloride ion. And this is actually the real compound. So everything that is inside the square bracket is called coordination sphere, which made out of ion and ligand. And we have the counter ion, which is outside the coordination sphere. And the counter ion can be positive and it can be negative depending on the types of the coordination sphere. If you have positive coordination sphere, then the counter ion is going to be negative. And if you have negative coordination sphere, then the counter ions is going to be positive. This coordination compound play a significant roles in various fields including chemistry, biology, and material science. So understanding the nomenclature is crucial for effective communication in chemistry. So what are the components of this coordination compound? The component of coordination compounds include a central metal ions and a ligand attached to it, as I explained. And the ligand can be neutral molecules or anions that donate electron pairs to central metal. So generally, when we ask to define ligand, the ligands, they can be a neutral molecules and they can be anions or even cations. So generally, a ligand can be a group of atoms which can be a neutral and which can also be charged. In the charge, it can be negative or positive that donate lone pair of electrons. So generally, the ligand donate electron pairs to central metal ion. And that is why ligands, they are called Lewis base, while the central metal ion, they are called Lewis acid because they accept lone pair of electrons. So the donor are Lewis base, which is the ligand, and the acceptor is a central metal ion, which accepts the lone pair of electrons. So the arrangement and the number of ligand around the metal ion define the compound geometry. So this is actually what we have. So this is the coordination sphere where we have cobalt as the central metal ion and we have ligands. And as you can see here, the coordination sphere here is positive. So therefore we expect to have the counter ions to be negative, as I explained earlier. This is the coordination sphere and this is the coordination number. It means that if you look at it here, the number of ammonia ligand here is 6. So, and then this number reflects exactly the coordination number. What is coordination number? Coordination number is the number of lone pair of electrons that is donated to the central metal ion. That is coordination sphere. So that is coordination number. So the number of lone pair of electrons that donates to the central metal ion is what we call coordination number. So that is why the coordination number of this complex is 4. Sorry, is 6, because there are 6 lone pair electrons that are donated to cobalt as a central metal ion. So then the naming of the metal ion. So metal ion in a coordination compound is named first in the compound's name. And if the metal has a variable oxidation state, then the coordination or the oxidation state is indicated by Roman numerals. So if you have the central metal ion, or if you have the coordination compound first, you also need to calculate the oxidation state of the central metal ion in the coordination compound. And usually that oxidation number is usually indicated in Roman numerals. So for the metal ions, the Latin names are used with specific endings for different oxidation states. So if you have metals ion that has Latin name, so we usually use the Latin names to indicate that central metal ion. And this is most of the central metal ions, they are transition metal. They can be of D blocks or F block. F block element, they are called inner transition metal. And then we have the normal standard transition or the normal transition metals which belong to D blocks element, starting from scandium and zinc. And we have 3 series of the transition metal. Yttrium and cadmium is also second series. Lanthanum and mercury is the third transition series. So then the naming of ligand. So when naming ligand, the ligand are named before the central metal ion in the coordination compound. So if you have ligand and you have the central metal ion, so you start with naming the ligands. Neutral ligands often retain their common names. So if you have the neutral ligand, then you can use their common names and name them. While anionic ligands, you typically end with O, nitrito, chloro, because they are negative ligands and they can return, or they can actually end with O. Then the neutral ligands, they usually utilize their common names. So if you have multidental ligands or chelator ligands are also named with specific prefix to indicate the number of binding sites. So like for example here, this is actually where we have anionic ligands. So you see all these anionic ligands, their names end with O. Like for example, bromide is now changed to bromo, chloride is changed to chloro, hydroxide is changed to hydroxo, cyanide is changed to cyano, nitrite is changed to nitro, oxalate is changed to oxalo. Then we have also ethylene diamine tetraacetic acid EDTA is also negative, so it also changed to ethylene diamine tetraaceto. So for the neutral ligands, they return their names, that is, they return their common names. Like water, the common names of water is aqua, ammonia is amine, carbon monoxide is carbonyl, ethylene diamine is still remain as ethylene diamine. So for the neutral ligands, they maintain their names. So the prefix for ligand, so if you have one, usually prefix are used to indicate the number of identical ligand present in the complex. Like for example, if you have one, you actually add the prefix mono if it is 2 di, if it is 3, it's 3. Let's say you have 3 molecules of water as a ligand in the complex, you can actually name it as triaqua. If it is ammonia, that is NH3, it's going to be triamine. If it is 5, it's going to be pentaamine. Like for example, cyano, if it is 6, it's going to be hexacyano. So for ligands that already have a prefix, That is those ligands that have prefix attached to them already. Then you can use Greek numerical prefix and are modified to avoid confusion. So you see, this is actually the Greek mono, di, tri, tetra, penta, hexa, hepta, octa. So all these are actually prefixes that are used in naming or in like indicating same ligand that are present in the coordination compound. So then now, the name of the coordination compound. So the full name of coordination compound starts with the ligand followed by the central metal ion. And the oxidation state of the central metal ion is noted in parentheses after the metal's name. So anions are named by adding ATE to the metal name if the complex is anionic. So let's see. This is actually some of the examples of the coordination compound with their names. So you see, if the coordination sphere is negative, then you are going to add ATE. You are going to add ATE to the central metal ion name. But for the positive, it's usually remain the way it is. Like for example, this number 1, the coordination sphere is positive, it's not negative. So that is why you don't need to add any ATE to the central metal ion. So of course, we have, if you look at the first one, you have cobalt at the central metal ion and you have water molecules, that is aqua. So because you have 6 molecules of water, that is why it is called hexa aqua. Remember that the neutral ligands are names with their common name, so that is why it is aqua. So water is neutral. So we have hexa aqua, cobalt, chloride. So you see the oxidation number is written immediately after the name of the central metal ion. So that is how it is. And of course, you have the counter ion. You have the counter ion as chloride. So it usually come at the end if the coordination sphere is positive. And then of course we have number 2 here, where we have nickel as the central metal ion, and we have ethylene diamine. So you see, we have diamine. So usually this kind of compounds ligand, you use tetraikis, tris, bis to name them. So like for example, here we have trees, because there are 3, that is why it is trees, ethane 1,3-diamine, and then you actually give the name to the central metal ion, which is nickel. So you don't need to add anything because it is positive coordination sphere. And also for number 3, we have hexaamine, because you have 6 amine. So that is why it is hexaamine chromate 3. So the coordination number or the oxidation state is 3 for the central metal ion, and then the chlorides as the counter ion is also came at the end. So now let me just give a simple example on how to calculate the oxidation number of chromium in this number 3. So you see, you have chromium, so you can name the chromium as X, which is unknown. We want to calculate the oxidation number of chromium in this, so let it to be X. And then of course, the ammonia amine is the neutral ligand, so therefore its oxidation number is 0. So we have we have to open bracket 0 times 6 for the NH3. There are 6 and it is neutral, so that is why it's 0 times 6. Then we have plus the oxidation number of chlorine is -1. So we are now going to set -1 times how many chlorine do we have? We have 3. Then we put everything in bracket, then it's now equals to. So if you look at the entire compound, it is neutral. It doesn't have any charge. So at the end, it's now going to be 0. So here is 0. Then we now have X plus 0 times 6 is 0, then plus times minus is minus, then we now have minus 1 times 3, so it's now going to be minus 3 is equal to 0. And if you now take this 3 to the other side, so x is now going to be plus 3, so the oxidation number is plus 3. That is why you have 3 as the oxidation number in parentheses for chromium. So, and then of course for those that have negative coordinations pair, that is those that have a contact, they have positive charge metal as a counter ion. So usually the central metal ion end with ATE because it is anionic. So because it is anionic complex, the complex is anionic. So the central metal ion is going to be end with ATE. So like for example, here you have to start with naming the counter ion first. So the counter ion is potassium, so you have to name it first. So you have potassium, and then you have the central metal ion and the ligand. So the ligand is cyanide, and it. So if you check for all those with a complex or for all those negative complex, they have counter ion that is positive, and you usually start with it. Like for example, let's look at this one. This one is neutral. So you just started because there is not any counter ion. Then you started with tetracarbonyl because you have CO2. Sorry, CO, and CO is carbonyl and they are 4. So that is why it is tetracarbonyl nickel, and it is neutral ligand. So that is why the oxidation number is 0. So the oxidation number of nickel in this compound is 0. So that is why it is 0. You have also pentacarbonyl ion. That is why it is also 0 because CO is also 0. So this is actually how to name this organic, this how to actually name this coordination compound, and I think it's simple. For those that actually have or that are the positive complex, you started with the ligand. You started with the ligand like hexa, aqua, cobalt, fluorides. You started like, for example, number 3 hexaamine, chromium 3. So this is actually how to name these complexes. So then the next thing now, we are going to look at some of other examples. So we have an example here where we have a complex of copper central metal ion where we have 2amine. Sorry, we have 4amine and we have SO4 as a counter ion. So the name is tetraamine copper 2. So copper 2 sulfates. So it is 2 because the oxidation number is 2. Here, the tetraamine indicate 4 ammonia ligand coordinated copper, and then the Roman numeral 2 indicates that the oxidation number of copper is plus 2. And how do you calculate that? I think it's simple. Let's assume that the oxidation number of copper is X. So we have X plus we have NH3. So in bracket, NH3 is 0. So it has oxidation number of 0. Then we'll multiply it times 4. Then plus the oxidation number of SO4 is minus 2 and it is 1. So we multiply it by 1. Then it's equal to 0. So then now X plus 0 is still X. And then we have plus times minus is minus. So minus 2 times 1, we have minus 2 is equal to 0. So we now have X is equal to plus 2. And that is why the oxidation number is plus 2 for copper here. So in conclusion, ladies and gentlemen, the nomenclature of coordination compound is essential for clear scientific communication. The mastery of this topic aids in understanding of complex chemical behavior and reaction. So continuous study of coordination chemistry is crucial for advancement in various scientific fields. So you can see this is ionizable ion. This is the central metal ion. This is a ligand here. And then we have also the counter ion, and the coordination number is 4. So, ladies and gentlemen, I think this video is going to be very interesting, and please don't forget to subscribe and join the YouTube community, and see you in the next video.